Everyone, welcome to the Planetary Sample Science Seminar Series, or as we like to call it. We're really excited to have our speaker today, Dr. Gordon Osinski. Again, Planetary Sample Science Seminar Series hosted by the Survey CASA Moon team. Everyone here at UNM, LPI, JSC, APL, UNM Grand Challenge. So thank you guys for coming in today. So for Dr. Gordon Osinski, he's a professor in the Department of Earth and Sciences at the University of Western Ontario, Canada. He's also the director of the Canadian Lunar Research Network. Dr. Osinski's research interests are diverse and interdisciplinary in nature, motivated by understanding the evolution of the surface of the Earth and other planetary bodies, as well as the origin and evolution of life. He is most known for his field and sample-based research on terrestrial impact craters, for which he was awarded the Behringer Medal of the Meteoritical Society in 2021. Dr. Osinski is also involved in several past and ongoing planetary exploration-related activities. He is the PI for the Canadian Lunar Rover, which is Canada's first ever rover mission to the moon, and is a co-investigator on the PanCam instrument on the European ExoMars mission to Mars. And Dr. Osinski has also been involved in providing geology training to Canadian and U.S. astronauts for the past decade. And of course, he was recently named to be part of the geology team for the Artemis 3 mission. And we can all not express enough how excited we are to have you here with us. And we are ready to learn about the nomenclature of lunar impactites and why we should care. So Oz, go ahead and take it away.
All right, well, thank you very much. There we go, back to the title slide. Yeah, thanks for the invitation to speak to the group today. And I know it's a little difficult to make it informal in this kind of online venue, but you know, if you really have a burning question throughout, please stick up your virtual hand, or I hope I left plenty of time for questions and answers at the end, because you know, what I'm about to talk to today is, you know, quite a big topic. There are many experts in the room that I would love to get feedback on. Okay, so first of all, some history. You know, how have we got to where we are today in terms of, you know, the naming convention for lunar impactites and particularly Apollo samples. So going back to 1980, this was kind of probably one of the first major contributions to this area. Paper led by Dieter Stoeffler, who unfortunately recently passed away from the Conference of Lunar Highlands Crust. And this was a recommended classification and nomenclature scheme. New Views of the Moon, the original volume. You can see many of the similar and same authors in this list. Richard Grieve, who is the last author in this chapter, actually saw Richard in Ottawa on Monday. He's still kicking around, and he and I have been working on the nomenclature of terrestrial impactites for a long time, since my PhD now. If you've got good eyes, and I'll give you a second, you know, the major classification probably didn't change too much between this 1980 paper and New Views of the Moon 1. In the meantime, though, a lot changed and happened, and in this lunar, and essentially the impact chapter in New Views of the Moon 2, we recognized that there were some challenges in the nomenclature of not just lunar impactites, but all impactites. And we tried to, you know, have a bit of a discussion in this chapter, and I want to continue that with you all today. First of all, you know, just for those who might not be aware, you know, impactites is the name that we give for all rocks that are not just produced, but affected by impact or shock metamorphism, or actually by an impact event in general. So, you know, how I got into this was studying impact craters on Earth. And I also do want to make this point in that, you know, our understanding of cratering processes has come a long way, just I would say in the last couple of decades. And so, you know, since the terminology was really defined kind of 50 years ago, we've learned a lot about cratering processes where these different types of impactites formed. And so I think it's, you know, quite a good time to have this discussion. I would also say, you know, part of that is due in the Apollo era. We only knew of about 30 or 40 confirmed meteorite impact craters on Earth. and the number is now 200. So part of this is just the increased awareness of impact cratering on Earth. We have a much bigger record, which means much more potential for collecting scientific data. If you're interested in this, I'll just do a shameless plug for impactearth.com. This is a database of all terrestrial impact structures that you can go to and browse at your heart's content. So again, my approach, I am increasingly working on lunar meteorites and Apollo samples, but I've had the privilege now, makes me sound old, but 25 years ago this past summer, I started my PhD fieldwork looking at impact craters. And I've had the opportunity to do, field work pretty much every year, apart from COVID, in craters around the globe. Many of them here in Canada, many of which are, really incredibly well preserved. This is this famous outcrop at the Kamastaston or Mastaston Lake structure in Labrador. You're looking at a cliff about 80 meters high, where you can hopefully see beautiful columnar joints. So this is impact melt. It's actually an impact melt pond in the rim of this particular structure. One that's a little less well known, but it is equally as spectacular and even larger, is the West Clearwater Lake impact structure in Quebec. There's a rock hammer for scale kind of in the bottom left. And this is a beautiful cross-section through a melt sheet of the interior of an impact crater. And you can hopefully see that this is a pretty clast-rich impact melt sheet. So, based on, these original papers and what we've learned in the preceding years, looking at terrestrial impact craters, we can kind of group, and I think this broad classification into three classes still stands. So we have shocked rocks, so these could be clasts in a breccia, or the example here on the bottom left are beautiful shatter cones in the central uplift of a complex crater. So the rocks in a crater rim in a central uplift, or as clasts in breccias and melt rocks, those would all be classified as shocked rocks. We then have impact breccias, which are probably, the most heterogeneous and broadest and potentially biggest category, especially when we look at the moon, of impactites. And then we have impact melt rocks at the other end member. And you'll see that this pretty much mirrors that broad classification from that New Views of the Moon book chapter that I've just put here on the screen. Okay, the devil is in the detail, as they say. And so this is a chart from Stoufler and Grieve, 2007, which is a recommendation. And, it was never fully approved by the International Union of Geosciences. So, just to kind of, I guess, emphasize the point, unlike most of the fields in geology, thinking igneous, metamorphic, and sedimentary in particular, we know what we mean when we all say a granite by grain size and geochemistry, or a sandstone. We do not have that for impactites. And so that poses still some considerable challenges. I would also add that, this classification, even though it was published in 2007, actually originated in the early 1990s, and not a lot changed in the meantime. And one of the biggest challenges is in this kind of area where we have impact melt. And so, in this classification, I get on WebEx if you can see my mouse, but you essentially have impact melt rocks that are, in one piece of the tree, and then breccias are classified separately, and we have this particular rock type shortened here to swavite. I would like to refer to it as an impact melt bearing breccia that is kind of totally separate. Now, the reality is that this is a continuum, and I think, this nomenclature here and this way of looking at things has actually hampered our, understanding of cratering processes. The best analogy I can think of is, in terms of a continuum would be, the plagioclase feldspar solid solution series, where, there's no breaks in this. We've arbitrarily chosen certain points to call, a plagioclase of a certain composition andesine or a northite, but there's no breaks. And in reality, again, going from a completely clast-free impact melt rock, 100% melt, to a breccia that contains particles of melt, it is definitely a continuum. As an example, this one little box here, we see this kind of rock type in just about every impact crater on Earth. But hopefully you'll agree with me that, the breccias I'm showing you on the screen are vastly different. Yet they've all been called soavites at one time or another. The bottom left is the type locality, the Ries crater in Germany. Far right is the Masthasten or Canasthasten lake structure in Labrador, where you can see these beautiful elongate particles of impact glass. Top middle, though, is Meteor Crater in Arizona. That is a breccia where you cannot see the melt. It is microscopic and it's maybe less than 1 volume percent. And so, is that the same type of rock as the one on the bottom right and bottom left? According to the current classification, yes. Another example is the bottom middle. This is the Onaping Formation from Sudbury. It actually can contain up to 50-60 volume percent melt particles, but it actually formed because you had hot impact melt interacting with groundwater that essentially caused melt fuel coolant interaction, shattered the melt, and dispersed it. So again, from a genetic perspective, it's a very different process as well. So a while ago, Richard Grieve and I, and again, this is old and I would revisit this myself now, kind of tried to come up with a bit of an alternative classification scheme for melt-bearing impactites that was more descriptive in nature, according to the ground mass texture on the left-hand side, borrowing and using a lot of terms that are well accepted from igneous nomenclature. Okay, so that is perhaps hopefully part of the rationale. Why it's more important than to just me. I want to kind of offer 3 main examples now. The first one, I've called accessibility and communication. And what I really mean by this, by accessibility in this usage of the word is, someone new to the field or someone who wants to get into the field looking at Apollo samples. We have, if you click on breccia, when you go to the lunar sample photo catalog, you get a whole bunch of different names, some of which even I have no idea what that particular breccia category is still to this day. Some of you in the room may be absolutely familiar after working on these for 30, 40 years, but I think there is a barrier for those either coming in completely new to looking at Apollo samples, but also people like myself that wanted to get into this from, looking at terrestrial craters where things are called different things. I would say it is also timely as well, because this is, I don't know if some of these authors are in the room or on the call now, but I know Jess Barnes and Katie Joy, I've talked with a bit about this recently, and they're working on a paper now. Those working on lunar meteorites have also been thinking about this too. And so, now's a very good time to be thinking about it more broadly than just lunar meteorites, but also Apollo samples and terrestrial impactites too. It is, of course, very timely. That's why this survey node is also exciting. We're going back for more samples, right? It's a question of hopefully when, not if now. And I'm, as well as being on the Artemis 3 science team, geology team, I'm also involved in helping to put together the training modules that the Artemis crew will receive. And this has actually already started. So on the left-hand side, this is me in the middle. I was up in the field with some of the Artemis 3 internal science team to this Canasthasten structure in Labrador last September, so about a year ago. Jeremy Hansen on the left is part of the Artemis 2 crew, and Canadian astronaut Jenny Gibbons is on the right-hand side. And then they're also undergoing classroom training. This classroom training will start as soon as the Artemis 3 crew is announced, which could be months. And then hopefully if none of the preceding things really caught your interest in the rationale, I would like to offer that, understanding the cratering process and where these Apollo and samples and meteorites came from would greatly, or our understanding of that would help if we were all communicating and using the same language. So this is definitely a topic which I'm super interested in collaborating with folks on. But I think we're getting to a point where, based on our increased knowledge of terrestrial craters, if you were to bring me a breccia sample that had, a certain content of melt or melt particles with a certain properties, either chemical or textural, or perhaps a melt rock with certain properties, I think we could have a much better, I was going to say guess, but it's more than a guess, much better idea now than 50 years ago of where in a crater this could have come from. And so, potentially when we're bringing back the new samples and going back through the old Apollo suite, a ballistic ejector from a crater of a certain size, I think should look a certain way. A melt rock from a crater-filled deposit of a crater of a certain size, I think should look a certain way and should have certain characteristics. And so, this is a work in progress in my head, but I'm looking to kind of, talk with lots of folks about this at a later date. Just to kind of zoom in on that diagram. So this is a diagram from a review paper that I recently led on terrestrial craters. It's in Earth Science Reviews from 2022, if you're interested. This particular slide there's a lot on it, but there's different settings of where we get different types of impactites. This particular diagram, which we have the added complication on Earth, is also looking at sedimentary, mixed, and crystalline targets, which at least for the moon, we don't have to take into account, at least to as much extent. Okay, so this is a work in progress. I apologize for the huge amount of text, so I'll leave it up on the screen for a little bit. This was is taken and synthesized from the impacts chapter in New Views of the Moon 2. And so what I've attempted to do here is on the left-hand side, taken kind of the original and still probably widely used breccia class, or impactite class, I should say, on the left column. In the middle, there's some characteristics, and then basically a recommendation that is largely based on, but not completely, on terrestrial impactites. So I'll go through a few of these now, not every row in detail, and then I've got some slides of Apollo samples where I hope to kind of showcase some of the things that we're discussing. So the fragmental breccia is a big one, especially given where we're going with Artemis, the lunar, the Apollo 16 analog. A lot of the rocks that we're probably going to bring back from the South Pole region are going to be fragmental breccias. As I'll hopefully show you in a couple of slides' time, we've learned when we look at terrestrial craters that there really are two main classes of breccias, and there are N members. And importantly, these different breccias are found in different places. So on the one hand, we have a lithic breccia that is melt-free, and at the other end is a impact melt-bearing breccia, or a swavite, which contains glass particles or clasts of hugely varying volume percent. A glassy melt breccia is a fairly common term from Apollo nomenclature. I think this and the next one are a bit more straightforward in that really, if the rock you have has a ground mass of impact melt, whether it be glassy or crystalline, it's basically an impact melt rock. And you can add a prefix for glassy, maybe the grain size as well, and then class poor, class free, class poor, and class rich. Impact melt breccia is a term we used to use for terrestrial impactites too, and is of course widely used in Apollo samples. I'm a bit more take it or leave it here, because I think most people probably understand that this is essentially a class-rich impact melt rock, but I'd be interested in getting the perspective from those on the line now. class poor melt rock, and then regolith breccias. I'll maybe open a can of worms at the end of this talk, and we can go from there. So I'm just going to step through clast-rich impact melt rocks. Again, I think this is one of the more simple things to do. You know, in getting into the Artemis astronaut training, I do think if we can start to call these what they really are, which is impact melt rocks, it actually simplifies everything. We just have some that are clast-rich, formerly impact melt breccias, but again, it's a continuum to those, you know, clast-poor and even clast-free melt rocks, of course, of which that end member, SPA melt, is what we expect. So, you know, impact melt from the South Pole Aitken Basin, which we would dearly like to bring back from Artemis 3, will likely be a clast-free impact melt rock. And so this is sample 72435. You know, some photomicrographs on the left-hand side. Quite clearly, it's fairly fine grained, but there's an igneous matrix with lots of lithic and mineral clasts. So a clast-rich impact melt rock. And, you know, a quick kind of definition there. There are, if you search impact melt breccia again in the lunar sample catalog, you do get some more unusual ones. And I don't actually have an answer myself for this one. You know, this is kind of a cool rock. Part of it depends on context, of course, and often when you're only seeing a thin section from a larger rock, you know, you might classify something in one way based on one thin section, but another way based on another thin section. And that's a challenge that we face, will always face. But this is, you know, a particularly interesting one that's currently classified as an impact melt breccia. And depending on where you look in the hand specimen, you could perhaps call it an impact melt rock, clast-rich, or an impact melt bearing breccia, which brings me to the next classification. Lithic breccias, again, I actually, you know, I think quite interesting because, you know, some people may not think they're as interesting because there's less datable particles, you know, often very little to no impact melt particles. On the moon, on Earth, of course, and I'll come to this complication later, we wouldn't get a breccia that has clasts of melt rock from a previous impact. We're typically talking single impacts on Earth. That can happen on the moon, but this is an example where there's very little melt content. And, you know, I think we've learned enough that on Earth, this only occurs in a couple of main settings. Volumetrically, by far the biggest is in ballistic ejector blankets for both simple and complex craters. So, you know, knowing that this is a lithic breccia will help us understand and figure out where potentially it came from and what we're sampling. Impact melt bearing breccias, again, it is a huge can of worms. Those that know me for work on terrestrial craters, you know, I started looking at the Reese crater in my PhD and opened the can of worms there with Richard Grieve, and that's still ongoing. This term swavite, impact melt bearing breccia, and again, on Earth and I think on the moon, there's a huge variety of impactites in this category, which I actually find super interesting. You know, one example is this rock on the right that is currently classified as an aphanitic impact melt breccia, so a fine-grained impact melt breccia. But when I look at this rock type, and this is from Boulder 1 at Station 2, which is super interesting because we have contacts and multiple samples, and has been the focus of some, getting the term right now, collaborative studies in the past and potentially in the future. You know, here's some thin section images, but if you keep that kind of view of the thin section on your right, this looks a lot like these melt-bearing breccias that we get in terrestrial craters. And so, you know, I'll show you a slightly, it's bigger than a boulder. I don't think there's a person on here for scale now I'm looking, but this outcrop on the right is from this the top, it's from the Camastaston Lake impact structure, again in Labrador. Quick aside, it's a fantastic lunar analog because a large part of the target rock is an orthosite. So not only do we have a relatively well exposed and preserved crater, we have an orthositic target rocks in part. And, if I switch back, between the right-hand side thin section and perhaps C and D in here, these are these quite complex breccias where we've got impact melt and lithic material, mixing together. This particular outcrop actually is the contact between class poor melt rock and underlying ballistic ejector. And so that's one setting in a crater where this particular rock type occurs. This again, I think, is something I don't have the answer for. If I'll maybe just quickly go back, if you'll bear with me. On Earth, we define these melt-bearing breccias in Dieter Stoeffler and Richard Greaves' paper. They use cogenetic melt particles, and what that means is melt generated from that impact, which again on Earth is straightforward. But on the moon, right, we have this added complication of, what if all the melt in here, which is likely many of the samples are from previous older impacts. Is that a lithic breccia, but with classes of older melt, or is it a melt-bearing breccia? And again, I'm happy to take advice on this one. And yeah, just before I open up for questions and a discussion, regolith breccias. And so, this is something that, is a newer area for me. And so I struggled quite a lot wrapping my head around what regolith breccias are. I understand on paper what they should be and how they're formed. And, when I see this kind of regolith breccia that has these beautiful, highly vesicular particles that we term the agglutinates, I'm like, okay, regolith breccia forms some very superficial impacts. That's one thing. And this came about, just somewhat randomly, because I requested a bunch of regolith breccias for a project, started looking at them, and they looked more like, impact breccias and melt-bearing breccias and even melt rocks from a lot of terrestrial craters. And, there's several examples we're looking at here at Western where, as far as I can tell, a lot of the classification comes from if they don't contain agglutinates, are not obvious ones, but they contain spherules. So you see this nice, perfectly circular glassy sphere, an impact spherule in this case. I just, want to throw up some slides on the screen. These are backscattered electron images now, so grayscale as opposed to photomicrographs from the previous screen. But hopefully you'll see in each of these, the top one you'll take a little bit of looking at, but all these spherical particles here are also spherules. These, I think, hopefully interestingly to the audience, actually come from the proximal ejector of the Ries crater in Germany. So these are spherules that were generated and incorporated in this upper melt-rich material as it actually flowed out of the Ries crater and on top of the ballistic ejector. So what you're looking at here, the red material in the base, or red brick red, is ballistic ejector. That's the so-called bunted breccia. And we have the overlying swavite or melt-bearing breccia that contains spherules. So perhaps, I'm just going to throw it out, some of the regolith breccias we've been studying in Apollo samples might actually represent, proximal ejector deposits from bigger complex craters. And with that, I am happy and looking forward to questions, discussions, comments.
Thank you so much, Oz.
And I don't know if it's easy for me to stop sharing my screen, or I'll at least make the people bigger on my screen.
It's up to you if you want to stop sharing it. I think it'd be easier to leave it shared. That way, if somebody has a question like that's in the presentation, you can just
For sure.
transition to it. But I guess we'll open it up to questions. So anybody here, does anybody have any questions, comments, concerns, testimonies? Chip?
Yeah, Oz, I just wanted to thank you for participating in this seminar series. I wanted to get you last semester and I finally got you this semester. So first, thank you very much. The question that I had was tied to magnesium sweet rocks, and the interpretation of their origin. And every now and then, there's a paper comes out that suggests at least some of the magnesium sweet rocks, like the norites, for example, could be impact melts from impact melt sheets rather than magmatic rocks in place of the crust. Do you have any recommendations or words of wisdom of how we can differentiate, a magmatic rock from something that is produced in a fairly large impact melt sheet?
Yeah, so I will add the caveat at the beginning, which is I have not myself studied magnesium sweet rocks from the moon, but I read about them. I'm aware of, some of the papers that you cite and, some of the history on them. And I have, no problem with some magnesium sweet rocks being interpreted as impact melt rocks. And that is primarily based on what we see at Sudbury. Sudbury to me is key. If you all haven't visited Sudbury, come up, visit me. Then it's just another 5 hours drive to Sudbury. It's a well-exposed crater. We originally think its structure was 250 kilometers across. So it's one of the big 3. And of course, it has this subeigneous complex that in places now we believe is actually up to 5 kilometers thick. It is differentiated. In most of the subeigneous complex, you do not see a single clast. And so, one of the kind of outcrop scale things you look for in impact melt rocks is typically clasts. But at Sudbury, the melt was so thick that they either, a combination of settling out, but more than likely assimilation, because you have a very hot, superheated melt rock. So if you were just to land down and be given a chunk of subeigneous complex, it's a coarse-grained igneous rock. That's why there was so much controversy about Sudbury for so many years. The geochemistry, for Sudbury, it's crustal. That's one of the arguments as to why it's an impact melt rock. But on the moon, that's a bit less clear cut to be able to offer that argument. Most of the subeigneous complex, apart from a few very bizarre isotopic systems, doesn't have an extraterrestrial contamination component. So that's, difficult if you rely on that. And then, I've thought about this a lot because, when you scale up to South Pole Aitken Basin or even, something along Oriental scale, impact melt seas, right? They're likely going to be differentiated. The volume of melt is just staggering. You're going to start partially melting the footwall rocks, the rocks beneath it too, and could have all sorts of things going on there. So, I guess a long-winded answer to the question is, when I look at some of these magnesium sweet rocks, at least visually, they look, and I could see how they could be impact melt rocks from a big crater. Easy ways to, differentiate between them. I think, I'm not sure there is one. Sorry. Maybe I'll just offer one other thing. There was the work that Clive Neal and Amy Fagan did on crystal size distribution, which did seem to suggest some differences between endogenic igneous rocks and impact melt rocks. Clive and I have talked over the years, and I think it'd be great if there's more work done, and in particular, actually applying that to terrestrial melt rocks where we know they're from a crater. And so I think, perhaps some more work done there might help in getting us further down the line.
Thank you, Oz. Does anybody else have any questions, comments? I know, Oz, you had asked the audience for input with some of the spreadsheets. So
Please comment, shoot me down, hopefully in a nice way.
I have a question.
Steve, go ahead.
Hi, Steve Simon here. You mentioned that there are class rich, class poor, and class three impact melt rocks. I've seen quite a few that seem to have like not enough class to call them class rich, but too many to call class poor. So shouldn't we have something in between, just an impact melt rock? Or do you recommend just picking one or the other?
Yeah, no, that it's great. You'd think we would have, and I've tried to search the literature going back, into the 60s and 70s, and I've bugged Richard Grieve about this, but again, I could imagine something where it's like, the Feldspar solid solution series where we just have to apply some numbers, Class 3 might have like 1% clasts, maybe class poor is up to 10, volume percent. Class rich could be over 30, then everything else in the middle is just a regular old impact melt rock. We don't have that, even that simple classification right now, I'm afraid. It's something I'm working on, and is also motivation for potentially getting something published in terms of recommendations.
I can see where that would work, to pick some numbers and stick with it.
Yeah.
Any other questions, comments, concerns?
Oh, another one.
No, Steve, go ahead.
Yeah, I did my PhD thesis on regolith breccias, comparing them to the local soils. And we found that the regolith breccias tend to have a lot fewer agglutinates in them. As fossilized soils, they probably preserved less mature soils than the present day soils, but it's also possible that agglutinates didn't survive the impacts, the lithification process. Looking in the SEM, I do commonly see little agglutinate fragments in the regolith breccias. I'm not sure what you were saying about agglutinates in regolith breccias, though.
I think I think when you see agglutinates, it's super helpful, and it makes them, to me, okay, I can absolutely see how that's a regolith breccias.
Sometimes people don't
A lot of regolith breccias I happen to have apparently got from Johnson Space Center contain no agglutinates and just spherules, and and I'm looking at these and I'm thinking, well, this looks more like a fragmental breccia or a lithic breccia than a textbook regolith breccia, which gets me thinking, maybe this is the proximal ejector from a simple crater on the moon versus formed from the regolith. So that's what's really got me thinking about this topic. I also was at a lunar meteorite 2 recently that we're looking at here that was actually classified as a regolith breccia initially, I think purely because it contains a bit of glass. Well, this glass looks to me more like the glass particles we see in these melt-bearing breccias in complex craters on Earth than an agglutinate. It's not very vesicular at all. And so, part of the final part of the talk was me wrapping my head around, what regolith breccias are and how they formed and, what that may mean.
And then for our folks online, does anyone have any comments, questions, or concerns? Yeah, go ahead, Carolyn.
Hey, Carolyn.
Hi, I've got my whole research group here. My question is just more like a logistical question, right? I mean, this seems like you said a very timely topic, and you are tapped into different aspects of the community, being on Artemis 3 geology team, and if there's recommendations coming out for meteorites, and is there a larger effort to or interest to coordinate these efforts to come up with a more common nomenclature between terrestrial and lunar? And I mean, there's gonna be breccias and other stuff on Mars and whatnot, not as many, but is there a bigger effort to do this?
I might turn that question around and ask this audience. I think so. Maybe I'll give you one answer. So there's actually quite a bit of interest within the Artemis science team in trying to nail a few things down, because if we're going to be teaching one crew one thing and one the other, or it's actually even more important, you know, for example, because the training's very modular, right? You know, I'm involved in a 10-hour block on impact cratering. Juliana Gross is introducing the astronauts to samples, right? So we got to make sure at least that her and I are talking the same language. Then there's another block talking about, you know, more regular igneous rocks. And so part of it is us trying to get together and making sure, you know, that Juliana's not using one term and I'm using another for the same rock. And I think that is important. So that is actually driving some of this in terms of trying to come to some consensus. You know, I actually don't know, and maybe I need to, I don't know if Jess Barnes and Katie or any of the folks in the lunar meteorite community are here. I think their impetus was just to try and make it easier for those classifying lunar meteorites in the initial classification anyway. So, you know, perhaps, and I don't know how that group got put together actually, whether it was volunteer or there was a session or something, but you know, if you and others on this call think it would be important enough, as I do, you know, maybe I can put out a call for interests and try to put together, you know, maybe an LPSC abstract and, you know, just set up an informal working group. I don't know if it would fall into, you know, a more formal group like League or something in the US. I would seek probably guidance from, you know, especially the likes of you, Chip, who have maybe done this in the past. But I guess, yeah, I might turn that around and say, I think it's important. I'm hoping if there's enough others that do, then, you know, I'd be happy to put the effort and pen to paper and try to get some discussion going.
Thanks, Oz. Yeah, I also wanted to punt to Chip and say, like, you know, there's two survey teams that are working on lunar samples, and is there a way that survey could help, or our teams could help
Yeah, maybe.
promote this or organize or whatever?
Carolyn, I agree with you. Again, this is Chip, that, you know, this is really ripe for, you know, a survey effort. And one could do this through the survey sample science working group. One could do it through that you're a member of. So there are a lot of ways we could partially do it through survey. And again, this is closely tied to getting great science, but also to enable exploration, which again is the goal for survey. So, you know, I'm on board to, you know, push this forward through survey if we get enough people interested.
Cool.
And of course, Oz, you're on our survey team.
Yep.
So that would wrap that really well.
Yeah, and it's, you know, maybe something that this survey team puts together, you know, a draft recommendation and, you know, brings it out to the community for comment and input.
Mm-hmm. And I know Jake Bleacher at NASA headquarters is really interested in some aspects of this. Like, he's really curious about how does one train astronauts to pick up the right samples. And I know that's a very general umbrella, but, you know, so, you know, he and exploration are interested in some of these, developing some of these areas or just exploration.
Yeah, for sure. And I mean, that's part of my motivation too, is not just the classroom training, but, you know, I think it's public and I won't get into trouble, but the Artemis astronauts should be going to both Meteor Crater and then Kamastaston Lake structure in Labrador. And so, you know, 2 of the 4 or 5 sites they visit will be impact. And, you know, actually going back to, sorry, I'm blanking who in the room made the comment, you know, they're given already like cue cards, you know, for classifying other rock types, but wouldn't it be great if they have one that has, you know, is this a class poor or a class rich melt rock? Well, if I know the percentage, that becomes way easier. You know, that's a very simple example, but it absolutely straddles science and exploration, this kind of the rationale for this.
Yeah. Any other questions?
Well, any other questions online or comments, concerns, testimonies? Yeah, well,
Yeah, I do have another question or comment to make. Again, this is Chip. What's very, we in the various survey groups and research groups throughout the world really have a lot of really great tools that one can utilize to study samples and analyze lunar samples. Like we have an individual group here that does oxygen isotopes, and they're utilizing those, at least with regular samples, to be able to determine process and impactor fingerprint. So that's really quite important. I know, we have a group of the other groups who are interested in dating argon ages for lunar events. But what's fundamental to all these measurements is kind of the work that you're doing in the classification scheme you're proposing. Because, I think there were perhaps some issues earlier on where some of this data was collected without placing the samples in the right petrologic, geological context. And again, I think that's what you and your group offer, which is just so fundamental to the work we do and the work that will be coming through Artemis 3 and 4.
Well, thanks for that, Chip. And, putting our heads together, everyone's heads together on this would be fantastic. So I'd be happy to keep the conversation going and reach out to some of you to see what we can do afterwards.
Right. And then one other question, I'm sorry. How is your work on Station 3 going?
I see.
Sorry, Station 2.
Yeah, I finally 2-3 weeks ago got a big batch of thin sections. So
Good.
I had did some initial work, but that will be ramping up now. I finally have the samples. Yeah, so maybe present on that in the new year to this group again.
Okay, that's great.
well, thank you again, everybody, for coming to the Planetary Sample Science Seminar Series. Please join us again next week, same bat time, same bat place. We have Steve Alardo next week. So again, thank you guys so much. Enjoy the rest of your days and enjoy your week. Have a good one, guys. Again, also, thank you.
You're welcome. Thanks, everyone.